Hello guys, welcome to a new lesson. If you're staying caught up and following the right order of things, the last thing you should have done would be the Unit 2 test. I hope that went well. Today we're starting a new unit, Unit 3. Slight change to the way I'm doing things. I'm calling this 3.1. I'm going to number everything from now on so that assignments and notes and worksheets well, assignments are worksheets, but the grade book and Google Classroom, hopefully everything will be coded the same. So this is the third unit, that's why there's a 3. This is the first lesson, that's the 1, so 3.1. So the topic today is graphing exponential functions. And before we get into it, I'm just going to compare with you visually the graph of y equals x squared. That's a quadratic equation. It's also called a polynomial. The graph is called a parabola, something you should be familiar with. So let's see that. Y equals x squared. And just the structure of that, x, the variable, is the base, 2, the number, is the power. An exponential function, that's kind of flipped. So we have the number as the base and the variable as the power. And let's compare that graph, y equals 2 raised to the, try that again, 2 raised to the x power. And now you get a different looking graph. It's that blue one. For a moment, for a little while, it looks the same. Like right in here, they're very similar. But to the far left, that blue graph, the exponential, runs asymptotically to the x-axis. It's sort of parallel. If we zoom in really close, really close, wow, that's really close, it never touches. It just hovers right above the axis. So if I do it this way, so there you can see that there's a space there and it's getting closer and closer. But as I move to the left and zoom in, you'll see there's always a gap or a space in between there. But it does keep getting closer and closer to the point where it looks like it's touching, but then you zoom in and you see there's still a space. So the x-axis is an asymptote. The right side shoots way up to space. It gets very steep. Now it never becomes vertical. It keeps going to the right to infinity. So the parabola, something you're very familiar with, has a minimum point at 0, 0. The left and the right go forever up and outward. This one, the exponential function, asymptote to the left and then goes upward and outward to the right. So that's the main difference. And all exponential functions have that same general shape. Now we will be trying to draw accurate graphs using a graphing utility, so I'm using Desmos. If you have a TI-84, you can use that as well. When you're transferring your graph to paper, you'll want to include any intercepts that you can find. The asymptote, you'll have to be aware of that. I always draw a dotted line to represent the asymptote. You don't have to, but it's not a bad practice. And then any integer coordinates, if you can find them. I'll talk about what that means. Also, I'm going to practice covering or explaining the domain and range as we go through this. So every problem I'm going to put a domain and range, and then on this answer key I'll have it modified to include the domain and range for every problem. Alright, so as normal, we will do the evens, you can do the odds, and this first problem is y equals 2 to the x, so I guess I didn't really have to delete it. Nope, not y equals x, y equals 2 raised to the x. Okay, so let's talk intercepts. There is a y-intercept right here. There is no x-intercept because, as I said, the x-axis is an asymptote. It never crosses it. It just gets really close to it. The right side shoots up to infinity. Now I said include integer points if you can find them. So these are decimal points, decimal coordinates. Everything's a decimal. We get right here, 1, 2. That is an integer point. So I'm going to include that, and if I can find others, looks like 2, 4 is another one, and then I think 3, 8 should be another one, or no, what am I saying? 4, 16. I think I skipped over 3, 8. There should have been one at 3, 8. And you don't have to do as many as I'm doing. I guess I'm just trying to drive home a point here. There we go. 3, 8, that you can find certain integer points, and when you include those, they help make your graph more accurate. So especially the side that goes upward and outward. The more of those points you have, the more accurate it is, but you don't have to do that many. As far as getting the other side accurate, you really can't. I mean, if I trace along here, these are all decimals, and as I go to the left, 0.01, I mean, Desmos rounds it off 0.05, and then eventually it'll say 0 just because it does not round to 4 decimal places. Just because it says 0 doesn't mean it equals 0. If I zoom way in, eventually you'll see there is a gap. So that does not actually equal 0. And if you zoom in, it'll round off further. So you got that going for you. So anyway, you just draw a line that runs really, really close to the x-axis, and that's it. You don't necessarily have to draw an asymptote, so I'm going to use a very light color to indicate where the asymptote is. Now let's talk domain and range. Domain is the x values of the function, and this function goes to negative infinity on the left, and it does go to positive infinity on the right. I know it looks like it just goes straight up, but it does continue to go outward forever. So the domain is all real numbers, or if you like this notation, you can call it negative infinity to positive infinity. I'm probably just going to go with the all real numbers when it happens, because that's easier to write. The range is the y values. So this goes up to infinity. The graph does go up forever, but it never crosses the x-axis, and the x-axis is 0. So the range goes from 0 to infinity. Now we put a parenthesis on infinity because you can never equal it. 0, well, what do we do there? Do we do a parenthesis or a bracket? Think about that. All right, got an answer in your head? If you said parenthesis, you are correct. Because this graph never touches 0, it never equals 0, you cannot have a bracket. The bracket means it actually reaches or touches or equals 0. Since it gets infinitely close but never touches 0, that's a parenthesis. By the way, infinitely close is not an accurate thing to say, but a lot of people understand when I say infinitely close, so I use that word. Now, before I go any further, that was y equals 2 to the x. Let me get it back on the screen. Oh, man, I'm just messing this all up. Y equals 2 to the x. If you compare that to y equals 3 to the... my gosh, this keyboard is not responding. 3 to the x. The graph is very, very similar. It's just steeper. The left-hand side is very close. Slight difference. The right-hand side still shoots up, but it shoots up steeper. If we change it to y equals 4 to the x, basically the same graph, but it gets even steeper than that. So if you increase the base, it makes it steeper. Just keep that in mind. Why would I want you to keep that in mind? Because look at number 4. Now we've got a fractional base. Y equals... Now, if I want to type this in the way it appears, I'm going to go parenthesis 1 divided by 2, and then outside the parenthesis, hit the power button, and x. Now look at that. This is essentially that graph flipped around. It is exactly that graph flipped around. How do I know? Because the denominator here is 2, and the base here was 2. So if you make this a fraction, it flips the graph vertically, flips it horizontally, flips it over the y-axis. So I can save some time by saying, okay, negative 1, 2, negative 2, 4, negative 3, 8, negative 4, 16, just like on the last graph. But you can always just run your finger along there and look for integers to pop up. And like I said, you can do 1 or 2 and you'll be fine just to get the general shape. I don't want you to draw something that looks like this when clearly the graph comes out here. But if you only do a couple of points and your curve is off a little, I'm not going to have a cow over that. That's not a big deal. So try to get your graph as accurate as you can. But there it is. There's our graph. The asymptote, if you want to sketch it in, again, I don't really care if you do or not. I think it's a good habit to have when you're making accurate graphs to sketch in an asymptote, but it's really, I don't know, never known it to be required in the world of mathematics. Anyway, domain, this graph does go all the way to the right to forever, I guess, and to the left forever, so negative infinity, positive infinity, all real numbers. The range, like the previous problem, it never reaches 0, So it starts there, but with a parenthesis, so it never touches it, and then it goes up forever. The y values go up to infinity. So that's the range. And gee, I haven't checked these answers yet, have I? So again, the domain and range, it's not actually part of the assignment. I'll be writing that in later. But there's my graph for number 2. There's my graph for number 4. All right, let's look at number 6. So now we've got the same graph as the first one, 2 to the x, but we're multiplying it by a negative number. So we got y equal, no, that's a minus sign, equals 2 raised to the x. So that's the graph that we had in the very first example. So the question is, if I multiply this by negative 4, what's going to happen? So let me put a times sign there, and in front of that I'm going to put negative 4. And that flipped it upside down. So the negative flips it upside down, but it also changed some of the key points. If it was just a flip upside down, then we'd have a y-intercept at negative 1, but we don't. You can see we have a y-intercept at negative 4. So we're multiplying every value times 4. That's going to stretch it out. So if I try to find another integer point, I'll be lucky to find one that fits on my graph. Maybe, what is that, 216? Or 2 negative 16? And yeah, nothing else is going to fit. So my curve looks like this. And then it just kind of, well, let's see, is there any integer point over here that I can use? Yeah, look at that right there. Was that negative 1, negative 2? Yep. Just cut it. So right there, negative, nope. Boy, I'm doing this all kinds of wrong. Negative 1, negative 2 is right here. So it's going to pass through that point. Is there another one? Negative 3, 0.5. It's not really an integer point, but it does help me draw an accurate graph. I still have the x-axis as an asymptote. So I'm going to draw my dotted line there. The domain, so I'm going to ask you to do the domain and range. I will edit the answer key so you can check yourself on this paper. The other paper probably won't have it because I don't edit those. I just edit the one that I'm working on right now. All right, so the domain, again, this graph goes to negative infinity, x value on the left, positive infinity on the right. Again, it looks like it goes vertical, but it does keep angling outward forever. So it does go from negative infinity to positive infinity, or what we call all real numbers. Now this time the range, the highest value it gets is 0, but it actually doesn't reach that asymptote. The lowest value that it reaches, well, it goes on forever, negative infinity. So our range goes from negative infinity, always start with the lowest number first, up to 0. 0 is like the ceiling, but it never touches 0, so you put a parenthesis on it. So that's what the graph for number 6 should look like. And there it is. Number 8. So now we have a fractional base times a negative number. Let's look at that. Y equals negative 5 times 1/2. Nope. 1/2. Oh, that 5 didn't show up. Man, this keyboard is touchy. Raised to the x power. Let me hit the home button, and there's my graph now. So it's kind of like this one flipped over, but it's flipped over and stretched out 5 times. So we have an intercept here. Oops. We have an intercept here. Do we have any other integer values that we can look at? What about 1? That's not an integer. 2. No, nothing really jumps out at me as being a helpful integer value. And sometimes that happens. What is there, one at 20 or something? Yeah, negative 220. Well, I'll take it. I mean, that's what I got to work with. So it's going to come here. And really nothing. What's that point right there? 0.5 comma 3.5. That's not very helpful. I don't know. If you find an integer value, if something jumps out at you, go ahead and use it. I'm just going to say, nah, and draw my graph like that. Sometimes you just do it. Here's my asymptote. Ironically, the domain and range for this one is the same as the domain and range for that one. If you look left and right, this graph goes negative infinity, positive infinity. If you look up and down, it goes negative infinity, but it reaches a ceiling or a limit at 0. It stops there. So domain, all real numbers, range, negative infinity to 0. So human beings look for patterns, and probably something is jumping out at you. Well, first of all the graphs are this general curve shape. They just are oriented differently. Is it safe to say the domain is always going to be all real numbers? Is it safe to say the range is always going to have a 0 and some form of infinity in it? Those are good questions. I'm not going to answer it yet. I'm going to say not necessarily. Here, let's look at number 10. And we'll just type this in. So what we've got 2 to the x, and again, that could be 3 to the x, 4 to the x, whatever. We're multiplying it by a positive number, so it's not going to flip it upside down. That's what negatives do. It's going to be right side up, but multiplying it by 3 makes it steeper. And then we're adding a 1 to it. So what is that plus 1 going to do? Maybe you have an idea. We'll see if you are correct. Y equals 3 times 2 raised to the x, and then I move the cursor over and hit plus 1. Hit the home button, and there's my graph. So I have an intercept right here. Do I have any other integer points I can look at? 1, 7 right here. Maybe do one more again. I don't need to do 5 or 6 like I always did on those other ones. What do we got? 2, 13. Weird that we're getting odd numbers. So I can say it goes like this. I could probably find one at 4, but I'm not going to worry about it. Maybe on the other side of the y-axis is there an integer point. Nothing really jumps out at me. Okay, so now it just kind of runs, makes its asymptote. But what is the asymptote here? What are the y values if I start tracing here? 1.02, 1.01, move way over and zoom in. 1? Do you think it actually equals 1? Or do you think if I zoom in enough, there'll be a space? Well, I gotta zoom in a lot, but there it is. There's a space. It does not actually equal 1. There's a space in there. So it looks like I have an asymptote at 1. So my graph is going to look kind of like that. So this plus 1 bumps the asymptote up from 0 to 1. So when you have a number added like that, that's going to move up the asymptote. What do you suppose would happen if it was subtracted? If it was minus 1, it would move down the asymptote, down 1. Now, does this change the domain? No, this thing still goes all the way to negative infinity on the left and all the way to positive infinity on the right because it does angle outward. So the domain is still all real numbers. Does it change the range from the other examples? And the answer is yes. If range is always low to high, the lowest number this reaches is not 0 anymore, it's 1, the asymptote. Although it doesn't actually equal it, so you have to have a parenthesis here. But it still does go up forever, so 1 to infinity. So the question I gotta make that infinity look a little better. So the question I asked before, is the domain always all real numbers and does the range always have 0 and infinity in it? Well, yes and no. The domain is always going to be all real numbers. There's really nothing you can do to this equation to change that. No matter what you add, subtract, multiply, divide, the domain will always be all real numbers. But the range can be some other number besides 0. It just depends on if there's something added like that. All right, now look at number 12. So now we have a fractional base. Remember, that flips it vertically or horizontally. We have a negative, which flips it upside down vertically. And we have a plus 1, but unlike the previous example, the plus 1 isn't in the base, the plus 1 is in the power. So will that still shift the graph up 1 and create an asymptote that is up 1? Let's type that in and see. Now this can be tricky to type in. In fact, I have a feeling the first time I type it in, it will interpret what I type incorrectly. So let's see. So I hit the power button, I need to type x plus 1. X plus 1. See how it put the plus 1 in the wrong spot? It moved the plus 1 down to the base. And we don't want that. We want the plus 1 to be up in the power there. So how do you do that? Well, one way to do it is to put x plus 1 in its own set of parentheses. Oops. And now that is accurate. Let me hit the home button and see, there it is. Now, did my graph shift up or down? No, it didn't. What does that plus 1 right there do? When you add up 1 to the x only, that actually moves the graph left or right. Oh man, I was just about to sneeze in the microphone. I held it back. Sorry guys. Okay. So this is the graph we need to draw. My asymptote is still clearly, hopefully clearly, the x-axis. So that hasn't changed at all. Do I have any key points that I can plot? Yeah, an x-intercept at 0, 2. Let me run my finger along there and look for any other integer values. -1, -4. That's a point. Probably going to be others. -2. Oh, I can't see. Oh, doggone it. My own finger was in my way. -2, -8, I want to say. Yep, -2, -8. And others. I'll just stop right there and say, and others. I'll just draw this. We get a good idea. Going to the left, does it look like one -1 is a point? Yeah, 1 -1. And then level off like that. By the way, I didn't check number 10, did I? Okay, when I check 12, we'll look at 10 and 12 together. Okay, domain, all real numbers. So now, on every problem, you know the answer for domain. It's going to be all real numbers. Range, it goes down to -infinity. It stops at 0, the asymptote. So 0 to -infinity. No, that's wrong. What I just wrote is wrong, but I did it on purpose. I really did, because a lot of students do this. When you do this notation, you have to have the smaller number here, the larger number there. 0 is not smaller than -infinity. -infinity is smaller than 0. So -infinity to 0 is the right way to write the range. Okay, let me check 10 and 12 both real quick. So 10, 12, good. All right. 14 and 16, and you probably get the point now. If you're done, if you're ready, go ahead and start on the rest of the assignment. What I'm doing here is kind of just going to be repetitive practice. So y equals 5 times 2 raised to the, now here I have to use parentheses, x plus 2, and then down here I have to put plus 1. Hit the home button. And there's my graph. Do I have a y-intercept? 0, 20 something. So that's way up there. It's not even on my graph. Do I have any integer points at all? Oops. Gosh, I don't see any integer points that we can hone it. Oh, there's one right there. So what is that? -2, 6. Oh boy, but that's all we got to work with. Where's the asymptote? The asymptote is at +1. So I can sketch that in with my yellow line. And now I just got to draw my curve. So it doesn't cross the y-axis until way up there. Curves out kind of like this. Domain, all real numbers, range. Lowest point to highest point. The lowest it reaches is 1, but it doesn't actually reach that. It's just a barrier, so there's a parenthesis, up to +infinity. Check number 14, and there it is. Pretty much the same. 16. Y equals 4 times 2 raised to the x plus 1 minus 2. Now my asymptote, if I hit the home button, is at -2. Can you see that? So that the -2 asymptote jives with that -2 right there. Where's my intercept? I have an x-intercept and a y-intercept here. So -2, 0, and 0, 6. Are there any other integer points? Probably don't need them. It looks like there might be one around 14 or 15. 1 comma 14. Okay, so this gives me a pretty accurate set of points to base my drawing on. Domain, all real numbers. That is a funky letter D. Let's make that look better. Range. My range is -2 to infinity. The lowest point is -2, but a parenthesis, not a bracket. Infinity, because it goes up forever. Check number 16. Looks good. Let's check number 18 before we finish. So it looks like we're going to have an asymptote at about +1. Let's do this. Yep, you see a +1. Okay, this has the number E. Boy, I told all those people, if you're done, go ahead and get to work. E. So people might have issues with this one. We're going to learn, I think, next week or maybe later this week about E. E is a number. I know it's a letter of the alphabet, duh, but it is a number. It's kind of like pi. It's different, but the idea is the same. It's this mathematical constant. To get E in this calculator, so I need to go times E. I hit the ABC button, and I just choose the letter E. Now I need to raise this to the power x minus 2, and then over here type in a +1. So what's my asymptote? My asymptote appears to be +1. Go ahead and sketch that in. So to get the number E, use the alphabet button and the letter E from the alphabet keyboard. Do I have a y-intercept? Well, barely. It's not an integer value, but whatever. Do I have any integer values that I can work with? 3, 2 looks like might be one. Right there. About 4. Nah, 4 just gives me a decimal. 5 gives me a decimal, but it's close, so 5, 7-ish. Yeah. We'll just call this, oops, good enough. Wow, look at that. It's awful. But you know what? I'm going to leave it. Just to illustrate the point that imperfections are okay. Domain, all real numbers, of course, because everyone is. Range, lowest point to highest point. Lowest point is 1, highest point infinity, parentheses on both, and that is that. Okay, I'm going to wrap it up. Feel like I've been talking forever. Contact me with questions. Good luck. Talk to you later.